Hello everyone. Today we're going to talk about bipolar junction transistors. BJTs is what they're called. They're very common. They're used in three-terminal devices, silicon devices, semiconductor devices. They're used in amplifiers and switching applications. We'll be looking at both of those types of applications today. As I said, it's a three-terminal device, and the three terminals are called the collector, the base, and the emitter. Okay, there's two main types of bipolar junction transistors, two general types. One is called NPN, the other is called PNP. They refer to the arrangement of the junctions. Okay, so it's like a sandwich. Okay, basically the NPN has two N pieces on either end, two doped so that they're N-type semiconductors separated by a thin P region. The PNP is the opposite. It's got two P areas on either side that are separated by a thin N region. Okay. The center part, the base, is lightly doped. And then the emitter and collector are more heavily doped, meaning they've got more holes or free holes or electrons, okay, or free electrons. Let's see if I can. So this is an NPN transistor circuit, all right, and what we do is we connect up a base voltage here between the base and the emitter. This is the symbol for a transistor. This is the base, this is the collector, and this is the emitter. The emitter always has the arrow, okay? And in this case, it's NPN. If it was PNP, this arrow would be faced the opposite direction. The base emitter junction is forward biased, as you see here, with the positive going to the base. And then the base collector is generally reverse biased. Okay, so the collector voltage here, its collector power supply is right here, and it goes through a current limiting resistor through the collector. And for a PNP type, everything would be reversed. So the arrow goes backwards, and this base voltage is reversed, as is the collector voltage. So the way these currents flow, all right, is they go for an NPN, the base current goes into the base and then down through the emitter, all right? And the collector current comes into the collector and down into the emitter. For PNP, it's the opposite. It comes up into the emitter, out of the base, and then again out of the collector. The thing to remember here is that with the NPN, the emitter current is the combination of the collector and the base. And the same for the PNP, only it's reversed. The emitter is splitting between the collector and the base current. Here's a curve showing the relationship between the collector current and the collector emitter voltage. Okay, so let me go back a second here. There's a voltage across the collector and the emitter terminals. You can measure that, all right? And that voltage and the current going through the collector and the emitter are controlled by the base current. All right, so spoiler alert, in a couple of slides we'll see that this base current controls the collector current and therefore controls the voltage across the collector and emitter. It's sort of like a variable resistor here. That's the way I like to look at it. It's like a potentiometer across the collector and emitter. And the knob on the potentiometer, on that resistor, is controlled by the base current. In other words, if you increase the base current, you drop this resistance across the collector and emitter. Okay, if you increase the base current, you drop the resistance between the collector and emitter. all right? If you reduce that base current, you increase the resistance between the collector and emitter. We'll see that in these curves. So this is a curve showing the relationship between the collector current and the collector emitter voltage. So it's basically a resistor, right? It's a current versus a voltage. Now this is at a constant base current. All right, so it's a single curve. All right, a single characteristic curve. We call them a characteristic curve for a transistor, showing the relationship between the collector emitter voltage and the collector current. And as you increase your collector emitter voltage, okay, so you're basically, what you're doing is you're turning up this voltage source, increasing it, all right? As you increase that, your collector current goes up. Now, it's not like a regular resistor. It is right here, okay, right in this range. But then it changes. It's still like a resistor, but there's a disjoint here, right? And then it goes into breakdown if you put too much voltage in there. Now, there's a saturation region here, and there's an active region and a breakdown region. We'll go over those in a minute, okay? Active region is usually where we operate in amplifiers, okay? Saturation is where we operate switches. So here's a family of curves. This shows different base currents. So understand that if you have a base current that is 0, that's what's called cutoff. And as you increase your base current, notice how the collector current goes up here. Clicks up, right? Okay, so you can keep a constant collector voltage, and you see, boom, 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 you increase your collector current. So this demonstrates how changing the base current changes the collector current. And the beta, it's called beta DC, is the ratio of the collector current to the base current. Usually that's a couple of hundred, that ratio. In other words, you can control a big collector current with a smaller base current. And that's the idea behind an amplifier. You feed an amplifier with a small current from a microphone, let's say, and the amplifier powers something that requires a lot of current, like a loudspeaker. Okay, so the loudspeaker is going to be connected up to the collector. The microphone is going to be connected up to the base. And a very simple amplifier. And we'll get into that next time. We'll make some amplifiers. So this is a little example of what's beta DC. This shows a family of curves, different base currents, 10, 20, 30, and so on microamps. And then this is the collector current, corresponding collector current. So they've chosen right in the middle 30 microamps, and that corresponds to about 5 milliamps. So 5 milliamps divided by 30 microamps is 167. And it's typically what we see on a lot of these transistors that we'll be dealing with. Between 100 and 200 is the beta. Now there's two regions or two conditions that that define the limits of a transistor's operation. One is cutoff and one is saturation. Okay, cutoff is when there's no base current, all right, and the collector emitter voltage is about equal to what's called VCC. It's the source voltage for the collector. Reason is there's no current going through the collector emitter, so therefore there's no voltage drop across it, so therefore everything, all right, I mean there's no current going through RC, this current limiting resistor, so therefore this voltage at this collector point equals VCC. So cutoff is basically when the switch is open, if you will. There's the potentiometer is completely as high a value as it possibly can be. Mega ohms, perhaps, okay? Millions of ohms. And we assume this current will be 0 at cutoff. The other end of the spectrum is saturation. That's when the transistor is, if you will, turned on as much as possible. It is going full blast. We have high base current, as high as it can go, and the collector emitter voltage is as small as it can be, maybe 0.2 volts. So the collector emitter voltage is actually VCC minus IC RC, the current going through the collector times RC. All right, that's the voltage drop across the collector resistor here. Now, the IC equals beta DC IB, all right, the multiplying the beta times the base current, that's no longer valid, all right, because it's in cutoff. Or I'm sorry, it's in saturation. We can draw a load line or a line. It's called a DC load line between cutoff down here. That's where IB, the base current, is 0. All right, and then up here where the collector emitter voltage is at a minimum, at a high current on the base. So you can draw this line. Now this is called a load line. And what I think is interesting about this is the way amplifiers work is that you kind of walk up and down this load line. If you increase the base current, you see how it hits these points? Well, this is a linear relationship. And as you increase the base current, you decrease VCE and increase IC in corresponding to the beta. Okay, so you have your collector current, which is in milliamps usually, and the base current, which is in microamps typically, and that's how the amplification occurs. But don't forget these 2 points: saturation and cutoff. Cutoff is when the transistor is completely shut off, and VCE, collector emitter voltage, equals the collector power supply, so it's completely open. And then the other end, where the collector emitter voltage is at a minimum and your collector current is very high. So here's an example. This is a great example. They're assuming beta DC is 200. So the saturation current is going to be VCC, and they're assuming 0.2 volts for the VCE SAT. They call it VCE SAT. So VCC minus 0.2 volts divided by RC, 15 minus 0.2 over 3.3K, is 4.4 milliamps. Okay. And then is the transistor saturated? Well, the base current is 3 volts minus 0.7. Where did the 0.7 come from? Well, it turns out that this base emitter junction is a diode. That's simple. It's a diode. It's a PN junction, just like the diodes we've been looking at. It's 0.7 volts when the transistor is operating. Now in cutoff, that isn't the case because you don't have any voltage or current going through the base, right? But when it's operating like this, you have 0.7 volts. It's a great way to test the transistor too. If you have a transistor, not sure it's good, hook it up to an ohm meter, put it on the diode setting, and connect between the base and emitter and see if you get a valid diode there, 0.7 volts. If you do, transistor's probably okay. Anyway, 3 volts minus that 0.7 for VBE, all right, divided by 220K, you get 10.45 microamps. Multiply that times the 200 beta, and you get 2.09 milliamps. Now, since that 2.9 milliamps for IC is less than 4.48, you know that that transistor is operating somewhere in here, not saturated. All right, it's below saturation. Because this 4.48 milliamps, that's up here. Okay? The 2.09, it's about half of that, somewhere in here. Okay? That's a good example. And you know what I do with good examples. I put them on exams. So it's a good example. No promises, but it might happen. Something like this will probably be on the exam though. So here's a data sheet, 2M3904, very, very common NPN transistor. There's a range of betas on this on these transistors between 100 and 300. It all depends on where you operate. You are operating on that DC load line. They're not perfectly linear, obviously, but here's a whole family of them. See, it depends on really on what your collector current is, 0.1 milliamps all the way up to 100 milliamps. Very common transistor, 3904. Good switchers. Okay, DC and AC quantities. Now we've been talking mostly DC quantities of these transistors, and they're annotated by capital letters, so V, capital C, CE in the subscript here. Okay. Now AC quantities are going to have small letters, lowercase, so VCE, small lowercase. And these internal transistor resistances are normally indicated as lowercase. So R prime E, for example, is the emitter resistance. And these are all equivalent resistances. They're not real resistances because you can't take an ohm meter and just put it across our and measure a resistor, right? These are just current voltage relationships that indicate resistances via Ohm's law. But you can't really take an ohm meter and stick it across a transistor and measure resistance. I mean, you can, but you're not going to get this value correctly, okay? Now, external, and we'll go into that more in a minute, but external resistances are indicated with capital R, and they are, you know, the collector resistor and the base resistor and so on. They're with capital letters, all right? If you're dealing with, again, if you're dealing with an AC resistance internally, or externally, it's going to be a lowercase c here in this case for collector. Okay, here's some amplifiers. Here's an amplifier. So here we have a sine wave feeding this NPN transistor. Okay, so we have a small sine wave at VBB. Okay, at VBB. It's imposed on the base supply voltage here. So this AC waveform is imposed on it through this coupling capacitor, okay? And that produces a varying current on the base current. So you're having this fluctuating sine wave current going into the base. Well, what that's going to do is create a fluctuating collector current. Okay, let me go back a couple slides here. So what we're doing is basically running a sine wave up and down these base curves. So this curve here is lifted up and down with the sine wave, right? And you ride this DC load line back and forth towards saturation and towards cutoff. More on, more off, more on, more off, okay? And as a result, you get this fluctuation in collector current, up and down, all right? And obviously corresponding fluctuation in the collector emitter voltage. And that's essentially how an amplifier works. So you get this small fluctuation in base current, resulting in a large fluctuation in collector current and a large corresponding fluctuation in collector emitter voltage. Now notice something, this is important. As the base voltage increases and the corresponding base current increases, the collector emitter voltage drops, right? Because you're moving towards saturation as you increase your base. So there's an inverse relationship between the voltages between the base and the collector. So higher base voltage, higher base current results in a lower collector voltage, but a higher collector current. So you're basically turning this transistor on a little bit or off a little bit with your base current. And we can use it as a switch too. A 3904 actually and 2222 and 2222s are often used as switches. And it's basically just operating a transistor between cutoff and saturation. I think the first lab in this chapter, we do this. We actually just look at some switches, basically logic switches using transistors. Okay, so in cutoff, we have an open circuit between a collector and emitter. In saturation, we have essentially a closed circuit between a collector and emitter. All right, very simple concept. And transistors are used in this capacity quite often. Rather than in a linear fashion, we use them in on-off nonlinear applications. A couple other special kind of transistors is photo transistor. Basically, it's a regular transistor, but they clip the base and then they put a piece of glass in front of the base, and as light shines into the base junction, what it does is it causes the collector emitter junction to conduct. Okay, so no light, we basically were in cutoff, and when there is light, we're basically in saturation. Okay, you can use these in linear applications, but not as often. Usually they're used optocouplers. I think that's the next slide here. Yeah, I'll get back. Here's an optocoupler right here. Phototransistor turns on a relay coil. Let's see here, optocoupler. Here, optocoupler. That has a LED, okay, in the same package, light emitting diode in the same package as a phototransistor. And you notice that if you add current or increase the current of the into the LED, it'll produce greater light, higher intensity light, and turn the transistor on more. There's no electrical connection between the input of this device and the output of this device. It's galvanically isolated. And we call a current transfer ratio as the difference between the output current and the input current. So the collector emitter current versus the diode current here. And these are used all the time, mostly in, matter of fact, some of you, if you're musicians, you're familiar with the MIDI interface, musical instrument digital interface. All MIDI devices have optocouplers like this. These are used in medical devices to isolate the patient from the electrical side of the world as a protection, and several other applications. Going back a minute here. So here's a little curve. Rather than having base current family of curves, you have a light flux intensity family of curves, which changes the collector current and the collector emitter voltage. Same thing, except for instead of base current, you have light intensity. And this just shows a little circuit that turns on a relay with light energy. So again, you can maybe this is in a 7-Eleven or something, a brake beam or whatever. It rings a bell when you walk in the store to interrupt the light, you know, that kind of thing. Let's see what else we got here. Optocoupler. Yeah, this is just for if you pass something through here, it'll interrupt. Again, this is a brake beam type of a application used in industrial controls quite a bit, you know, and paper copiers and things like that, you know. Anytime you have to take a physical object and move it through something without any friction, you can use a optocoupler. This is what transistors look like. Okay, they're 3-terminal devices, and they come in all shapes and sizes. This is a surface mount one. It's called a SOP23. Pretty common. No leads, just pads. You stick them down on pads, solder them down. This is a TO92 style case, 3 terminals. You can recognize the terminal arrangement here. Notice there's a flat side and kind of a round side. The flat side, the face I call it, the terminals are numbered 1, 2, and 3. If you remember EBC across the face, EBC across the face, that's how you'll always know. EBC, base is in the middle, collector on the right, emitter on the left. For the TO18, not real common these days. Okay, the emitter is usually this little tab here. And then the TO220 and TO225, they kind of get mixed up sometimes. It's sometimes the base is in the middle, sometimes it's on the side. For a TO3, this is a big one. Notice these have places where you can put a bolt or a screw. This one has 2. This is for higher power applications, meaning that the collector current and the collector emitter voltage are much higher. That's the power in a transistor, right? Power is what? Voltage times current. So if you take the collector emitter voltage, multiply it times the collector current, that's the power that the transistor is dissipating. Okay, and think about that for a minute. In cutoff, what is the, in true cutoff, what is the power being dissipated in the transistor? Well, in cutoff, you have no collector current, right? So theoretically, the power is 0. What about saturation? Saturation, you have a high collector current, but you have very low collector emitter voltage, right? So once again, the power is very low. So in cutoff and saturation, the power that a transistor is dissipating is very low, relatively low. Whereas anywhere in the middle, in the linear region, a transistor power dissipation could be quite high. And that's why there is these mechanical elements here that allow you to bolt these transistor cases, these 3 in particular, to a metal enclosure or a heat sink. So a TO3, you can dissipate many, many watts. Same with the TO220 and to a lesser extent the 225. And this is what I was talking about earlier about the diode test for your DMM, digital multimeter. For an NPN transistor or PNP, you can use either one. You connect it up and put the meter on the diode test, okay? And you should get 0.7 volts. And then reverse the leads and you should see an open circuit. Okay. All right, that's it for today. Those are the basic BJT, bipolar junction transistor treatment. And next time, I believe we start talking about amplifiers. We're going to put some circuits together, okay? Post your questions in the discussion section, and we'll see you next time.